In this video, we're going to take a look at calculating the arc length for a given function. And so first, just a quick visual to draw. We have a continuous function that we're going to close off between values a and b. And the first thing we're going to bring up is, let's think of how we calculate the overall change vertically for this function. The overall change in the y value given x. Well, that would simply be our y value at b minus our y value at a. But what if instead we wanted to look at the length traveled along the curve, kind of like distance traveled? And think about it like a roller coaster. Instead of looking at the height that we've changed vertically, we want to figure out how much track we've gone along. And the idea for that is calculating what's known as arc length. And the first thing we're going to need to understand is how we typically calculate the distance between any 2 points, x1, y1, and x2, y2. And our distance formula is the square root of the difference between our x's plus the difference between our y's, each of those quantities squared. It comes directly from Pythagorean theorem, but unfortunately this is only good for straight line distance. So what if we took a very small portion of this curve and we blew it up, we moved in very close, and we looked at the distance between 2 points here, x1, y1, and x2, y2, at a point where this does look like a straight line. And we make it so small that we really end up with some small change in x or dx, and some small change in y, dy. Then the distance for an infinitely small length of curve like the one we have here would be the square root of dx squared plus dy squared. And to calculate the arc length for an entire function over an interval a to b, we would simply integrate that distance formula from a to b. But the only problem with that is that with the calculus we're using, we can't calculate this because we would need this to be times dx times dy. We would need to integrate with respect to something, some axis. And so what we'll do is a little bit of algebraic manipulation. Let's go to try to get this set up to be times dx. And the idea is, out of those two terms, let's factor out a dx quantity squared. So that we're left with dx squared times the quantity 1 plus dy dx quantity squared, which would allow us to split this into two radicals, square root of 1 plus dy dx squared times the square root of dx squared, which would become the square root of 1 plus dy dx squared times just that dx that we want for our integral. And if that's the distance for one small portion of this graph, we would simply integrate that from a to b. And what this means is that given f of x is a continuous function on the closed interval a to b, the arc length of f of x is given by the integral from a to b of the square root of 1 plus f prime of x squared times dx, changing that dy dx notation into f prime notation. And so this is essentially just Pythagorean theorem done on a very small scale, and then the power of integration allows us to take that small scale calculation and apply it over a much larger interval. And all we're going to do is end with one example. Let's say we want to find the length of the curve f of x equals x squared from x equals negative 1 to x equals 2. We have our f of x equals x squared, and for arc length, we need to know our derivative, and in this case, f prime of x is just equal to 2x. So the arc length would be given as the integral from negative 1 to 2 of the square root of 1 plus the quantity 2x squared times dx, which would become the integral from negative 1 to 2 of the square root of 1 plus 4x squared times dx. And notice that u substitution would not work for this function, And we're not really concerned with calculating by hand anyway right now. The whole point is to gain appreciation for and learn how to use the formula for arc length. So I'm just going to run that calculation through a calculator, Math 9 on a TI-84, and get that the length of our curve from -1 to 2 is about 6.126. So that's it for this little lesson on arc length. Please go out and try this for yourself, and thank you for watching.